In the previous video, I asked if you could go through and try to work through this proposed equivalency, not quantity P and Q is equal to not P and not Q, and to determine if it's a valid or an invalid equivalency. Now notice that we only have two statements. So since n is equal to 2, 2 squared is going to be equal to 4. So n equals 2, which implies that the number of rows that we're going to have is 4. So in this one, we're only going to have 4 rows, which is nice because it's going to take half the time. So we have a P and we have a Q, and true, true, false, false, and then true, false, true, false. Right? And what that does is it gives us all 4 of the different permutations possible. Both P and Q are true, both P and Q are false, P is true, Q is false, or P is true, Q is true, and the other one's false. All right, so eventually we're trying to work from the left-hand side and see if it's equal to the right-hand side. All right, so we have P and Q, and remember that P and Q is only true when both P and Q are true. So we have true, false, 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 but then we have not for the left-hand side. So we're going to have not P and Q. So we just take the negation, and that's going to give us false, true, true, true. Right? Now, to get the right-hand side, it might be helpful to us to have not P, and it also might be helpful for us to have not Q. Now, not P is going to be false, false, true, true. And not Q is just going to be the opposite or the negation of what's in the Q column. So that's going to be false, true, false, true. And to get to our right-hand side, that's going to be not P and not Q. Right? And the only time that that's true is when they're both true, right? Because it's an and. So right here, they're both true. But in every other instance, we have at least one false. And we're trying to determine if the left-hand side is equal to the right-hand side. And right away, we can even see that those two middle are not the same. So right here and right here, those are 2 rows that are clearly not the same. All right, so what can we say? So that means that since the left-hand side is not logically equivalent to the right-hand side, that means that the negation of P and Q is not logically equivalent to not P and not Q. Or we can say the original equality is false, or the original equivalence. All right, so make sure that when you're doing these problems that you both justify by going through the process and then also write about and communicate what it is that you're actually getting for your solution. All right, now, what have we learned about the truth table? It's effective, but it's also cumbersome, and it's also prone to copy errors, and it just takes a long time. Now, what if we started doing 16 rows? Or what if we started having a lot longer sorts of statements? Well, then this becomes ineffective for us. So we have another way to determine if 2 statements are logically equivalent to one another, and that's by using Boolean algebra. We have all these rules. All right, and how do we know these rules are true? Because all these rules are indeed true. Well, what you could do is you could verify each of these with a truth table. In fact, you might recall that P or Q or R equals P or Q and P or R. Right? So you might remember that all the way back up here, we actually showed that. Okay, so we use a truth table to verify this, all right? And we've actually proved one of the laws, the distributive law, or at least one part of the distributive law. And that's how you would prove all of these, all right? Now, I'm not going to ask you to prove all of these. Let's just assume that somebody went through and they proved all of these for you. Now, in all of these statements, or all these equivalencies, excuse me, P, Q, and R are simple or compound statements. They're just some sort of statements. You see this capital T, that's a tautology. See the lowercase c, that is a contradiction. And what we're going to do is we're going to use these rules to perhaps make one side look like the other side. We're just going to simplify. So let's take a look at a really basic example of this. Right? So we have P or, not Q, and that's going to be equal to Q, maybe. Right? A suggestion might be is to always start in the parentheses. All right, so the first thing you always want to do is simplify what's in the parentheses. And what you can do is you can use De Morgan's law, right? So if you have a negation on the outside of parentheses, we have De Morgan's law, which basically says you're going to negate each statement and you're going to flip the quantifier over, right? So we can say that by using De Morgan's law, that the statement now becomes P or, and I'm going to do what we actually, the De Morgan's law, I'm actually going to do that in orange. So that's going to be not P and not Q. All right, so, and that's supposed to be equal to Q, all right? And the justification for that is De Morgan's law. All right. When you do these problems, make sure that you not only do the Boolean algebra, but justify each step. The next thing we're going to do is a pretty easy one. We have a not Q, and you can right away see that if you have not P, that's equal to P. So not Q in turn is just going to be equal to Q. All right, and that's a double negative law. All right, so once again, what I'll do is in orange, I'll just take care of the parts that I'm actually doing the Boolean algebra on. So this is going to be P or, not P or Q. I meant to do that in orange. So right here we had a Q, and that's going to be equal to Q, maybe. And that's our double negative. All right. So now that we have this simplified a little bit inside the parentheses, and I don't think we can do anything else to simplify that, now we're going to look for a pattern where we might have two ors, all right? And the only thing that we might have up here that has two ors in it in succession is this associative law, right? So what we're really doing is we're looking for patterns. So we have P or Q or R is equal to P or Q or R, so we just move the parentheses around, all right? So by the associative law, I'm just going to move the parentheses, and everything else is going to stay the same. So parenthesis here, and we still have P or not P or Q, which is equal to Q, maybe. All right, and that's going to be our associative law. P or not P. Well, if the sky is blue or the sky is not blue, it's got to be one of those two. All right, and right here we have, if we have P or not P, that's equal to a tautology. So that's nice. That helps us out a lot. So now this becomes tautology, or Q, is equal to Q. All right, and that's right here by the negation law. P or not P is equal to T. So that's our negation law. And then finally, the last one that we have tautology or Q is equal to Q. So notice that right here, where we have a tautology and or we have a tautology or right here by universal bounds, that's going to be equal to a tautology. All right, so what does that mean? So that means that this is going to end up being tautology is going to be equal to Q. All right, and that's by our universal bounds. And clearly that's not true. All right, so unfortunately, what we'd have to say for this one is that it is not valid. All right. So unfortunately, even though we got really close, the rules suggested that this is not a valid statement, right? So we just disproved it. All right, in the next video, what we're going to do is we're going to take a look at two more of these types of Boolean algebra problems and show you the patterns as to how to go through